Okay, this video is going to cover some examples from chapter 4, probability. Some very basic stuff, nothing too crazy. Probability does get difficult when you get into higher level statistics, but for now we're just covering some of the basic concepts of probability. Alright, so let's get started. Question number 1 says describe the sample space for each of the following experiments. So your sample space is basically like your total outcomes. Like what could you possibly get if you were to roll a coin or toss a coin or roll a die or something like that? What are your possibilities? So in part A it says, well, if I toss a coin, and it's just your standard normal coin, the only choices I can get is either heads or tails. I can't get anything other than that. So that's our sample space. Now, if we were rolling a die, our sample space would be like 1, 2, 3, 4, 5, 6. Very basic. The next one's a little bit trickier. It says if we were to select a student at random from a list of 10,000 students at a large university. So when we say our sample space for this one, we want to kind of be specific. So I'm going to say that the sample space is every student from the list of 10,000, from the large university. Alright, and so again, your sample space is just very, very basic. You're just simply listing out all your possible outcomes in a particular situation. The next question says, a fair die is rolled. Find the probability that the number comes up odd. Well, if you roll a die, your total number of outcomes already discussed as our sample space. That's 1, 2, 3, 4, 5, 6. But if I want the number to be odd, we're only specifically looking at 1, 3, and 5. So our final probability would be the total number of odd over your grand total. Well, we have 3 total odd choices with a grand total of 6 choices. So that would be 3 over 6 or 0.5. 50%. Next question, it says, in the Georgia Cash 4 lottery game, a winning number between 0000 and 9999 is chosen at random, with all possibilities being equally likely. What is the probability that all 4 digits of the winning number are the same? Well, again, I need to calculate out the grand total. So our grand total would be 10,000. And the reason for this is because our first choice, our first digit, we have 10 different choices with either 0 to 9. So I could choose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 for that first choice. Then the second digit, I have those same choices, 0 through 9. And so on all the way to the fourth choice. So I have 10 choices for the first one, 10 choices for the second one, 10 choices for the third one, and 10 choices for the fourth one. If I multiply out these choices, I get a total of 10,000 different number combinations. Now, if I want the number to be the same, so all zeros or all ones or all twos or all nines, and so on, like all threes, whatever, if I want them all be the same, I have 10 different ways of this happening. Because all zeros will be one way, all ones will be another way, all twos will be another way, all threes will be another way, and so on, all the way up to all nines. That's 10 different choices. So if I want to figure out this probability, again, I'm going to take the number of ways that the numbers are all the same numbers, so those 10 choices, and I'm going to divide it by my 10,000. Alright, and if I do that, I should get 0.001. Alright, next question. It says, a family has 3 children. Denoting a boy by B and a girl by G, we can denote the gender of these children from oldest to youngest. For example, GBG means the oldest child is a girl, the middle child is a boy, and the youngest child is a girl. There are 8 possible outcomes: BBB, BBG, BGB, and so on. Assume that these outcomes are equally likely. So the first question says, what is the probability that what is the probability that there are 2 girls? So here I highlighted in yellow all the different ways to get 2 girls. So here I have boy, girl, 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 boy, girl, or girl, girl, boy. Well, there's 3 choices out of those 8 choices. So 3 out of 8. And I'm going to go ahead and leave it as a fraction. I typically leave my answers as a fraction unless they specify for me to change it over to a decimal. The next one says, what's the probability that all 3 children are the same gender. So for them to be the same gender, we have to have boy, 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 or girl, girl, girl. I highlighted in green those two outcomes, and I can clearly see that there's 2 out of the 8 outcomes, or 2 out of 8, which reduces to 1 out of 4. All right, next question. It says there are 10,000 families in a certain town. They are characterized by their type of housing as follows. So we have this little table, this little chart, and they broke it down by owns a house, owns a condo, rents a house, or rents an apartment. Um, I went ahead and calculated out the total just to make sure, but they already told us the total from the very beginning was 10,000. So if you add them all up, you should get 10,000. So the question says, what's the probability that the sample family owns a house? Well, owns a house, they said there were 4,753 people that owned their own house. So the probability would be owns their own house over the grand total, which equals 0.4753. Next it says, what's the probability that they rent? So you have to be kind of careful with this one, because renting, you have to count in rent a house, and you have to add that to renting an apartment. And again, you divide that out by the grand total. So if I add that up over here on the side with my calculator, so 912 plus 2857, I get 3769 out of that grand total. And that should equal 0.3769. All right. All right. So the next question says, in a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Is this an unusual event? Well, in this class, we denote or define an unusual event as the probability being less than 0.05. So we say if the probability is small, small being less than 0.05, we think that it's an unusual event, or we think it's weird that that happened. So what we're going to do to figure out if this is an unusual event is, first we're going to calculate the probability. So we're going to take the 150 math students, we're going to divide that out by the grand total of 5,000 students. All right, and again, we're going to calculate that actual decimal so we can know if it's less than 0.05. So I'm over here on my calculator screen, dividing it out, and I get 0.03. All right, so now you want to ask yourself, is 0.03 less than or greater than 0.05? In this case, yes, I would say yes. The probability of selecting a math major is an unusual I can't spell, event, because the probability is less than 0.05. Now keep in mind, this is not like a hard and fast rule. It's just a rule of thumb. Depending on the situation, depending on the real life situation, your unusual event would be like 0.01 sometimes, or 0.10. Really just depends on the situation, depends on the field. Medical fields have a different probability for unusual events. But for us, our rule of thumb is just going to be 0.05. All right, so the next one says the Centers for Disease Control and Prevention reports that in the year 2002 there were 2,057,179 boys and 1,963,747 girls born in the United States. It says approximate the probability that a newborn baby is a boy. So what we're going to do is take the number of boys and divide it out by the grand total, which would be the sum of the girls and the boys. So again, over on my calculator screen, I'm taking my boys, and I'm going to divide that by the sum of the boys and the girls. and we get a probability of 0.5117. This probability seems pretty accurate, being that most people would think that you'd have about a 50% chance of getting a boy versus getting a girl. Alright, next question. It says use your chart to answer the questions. What is the probability that a randomly selected adult is likely to vote and favors the law? So, first of all, I needed to figure out what my grand total was. So I added up all the values in the chart to get a grand total of 1,000. Now, if I'm looking for the probability that the person is likely to vote and favors the law, I'm going to favors the law and likely to vote, and I'm finding that cross number, which in this case is 372. So I'm going to take that 372, divide it by my grand total, and I should get a probability of 3.372. Next, it says, what's the probability that a randomly selected adult is likely to vote? Well, likely to vote is whether, like, I care less if they're in favor or opposed to the law. I don't care. I just want to know if they're going to vote. So what I do is I add up all the people that are likely to vote, and again, I divide that out by my grand total. So 721 divided by my 1,000, I get a probability of 0.721. Similarly, if I wanted to find out the probability that a person favors the law, I would add up everyone that favors the law, which is 523, and I'm going to divide that out by my grand total of 1,000 to get a probability of 0.523. Next, it says use the general addition rule to find the probability that a randomly selected person is not likely to vote or undecided. So first thing I did was I calculated how many people were not likely to vote. Then I calculated how many people were undecided. Now, your general addition rule basically says that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. In other words, in this case, we're looking at the probability of not likely or undecided. And so that would be the probability of not likely plus the probability of undecided minus the probability of both. Alright, so if I was to actually calculate this out, I would get that my probability of not likely is 279 out of the 1,000. So 279 out of the 1,000 plus the probability of undecided is 112 out of the 1,000 minus the probability of both. So if I go back up here to the table, not likely and undecided is 25. So 25 is the both. So I'm going to subtract out that 25 over the 1,000. Alright, so if I add them all up, since I have a common denominator, I can just focus on the numerator. It should be 112 minus the 25. So I'm getting 366 out of the 1,000, which is 0.366. Alright, next we have in the 2008 Olympic Games, a total of 11,028 athletes participated. Of these, 596 represented the U.S., 332 represented Canada, and 85 represented Mexico. What is the probability that the Olympic athlete chosen at random represents the United States or represents Canada? So basically, representing the United States or Canada would be, if I add the United States, which was 596, plus Canada, which was 332, and divided it out by my grand total of 11,028. And so if I do that, and notice I don't have to subtract off any overlap, for the simple fact that these things are mutually exclusive. In other words, I cannot compete as a U.S. citizen and a Canadian citizen at the same time. I'm one or the other. So I don't have to subtract off anything that's overlapping. All right, so if I add those up divided by the grand total, I get 0.084. Now, if I want to know the probability that they're from US, Canada, or Mexico, I do the exact same thing, except for this time I'm going to add up all three. So 596 plus 332 plus 85 divided by that grand total. Alright, so again, if I take that over here, add the 596 from the US, plus the 332 from Canada, plus the 85 from Mexico, and divided by the total amount of athletes, which was the 11,028, I get a probability of 0.09. Alright. Alright, so according to the Wall Street Journal, 42% of cars sold in the United States, or I shouldn't say United States, but 42% of the cars sold in May 2008 were small cars. What's the probability that a randomly chosen car sold in May 2008 was not a small car? Well, either you're a small car or you're not. So if 42% were small cars, then that means 1 minus or 100% minus 42% were not small cars. So we're going to simply do 1 minus 0.42, which would equal 0.58 or 58%. Alright, so again, either you are or you aren't. So if you're not, well, then you simply just do the 1 minus as an easy way to calculate it. We use the 1 minus quite often in statistics to get an easier, quicker calculation for stuff. We don't have to just simply calculate it out. We can take, if we know the negative or the complement, we can just subtract it off. All right, so the next question says, the table presents the number of U.S. men and women 25 years or older who have attained various levels of education as of March 2007. A person is selected at random. First question says, what is the probability that a person is a man? So again, I'm going to add all of them up and divide by the grand total. So let's go ahead and add everything up right now to get the grand total. So I'm going to do, these numbers are kind of small, but 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1. And then I'm going to go ahead and add up the women as well. So 13.7 plus 39.9, or sorry, 31.9 plus 17.5. 9.6, 19.2, and 9.1. Alright, so I literally have to come over here and add all this stuff up. Give me a second while I do that. Sorry, it takes a while to type into this calculator. And I'm getting a total of 195. Alright, so the probability that they were a man, or the person was a man, is going to be the total number of men, which again I have to add that up. So 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1, and I'm getting 94. So I'm going to have 94 over that 195. And again, just typing it in to get the decimal equivalent, since that fraction is not really a useful fraction. It's not something I could tell off what it is. So I get 0.482. Alright, so the next question says, what's the probability that a person is a man with a bachelor's degree? So a man with a bachelor's degree, if I go to the table, for men, bachelor's degree, I have 17.5. So I'm going to do 17.5 divided by that 195, and I'm going to calculate that out. And we get 0.0897 or 0.09. Alright, so the next question says, what's the probability that a person has a bachelor's degree given that the person is a man? So the probability that they have a bachelor's given that the person is a man. Well, that formula basically says you want the probability that you have a bachelor's and you're a man divided by the probability that you're a man. Alright, so basically they're telling us to find the probability of both divided by the probability of the second, the given, which is the man. So I'm going to do 0.09 divided by 0.482. Alright, so again, over here on my calculator screen, 0.09 divided by 0.482, we get 0.1867. Alright, so next one says, among those who apply for a particular job, the probability of being granted an interview is 0.1. Among those who interview, the probability of being offered a job is 0.25. Find the probability that the applicant is offered the job. So again, this is another one of those conditional probabilities, because in order for you to be given the job, you had to be interviewed. So what they're really asking is the probability of getting the job given that we know you were interviewed. And so again, that is simply the probability of getting the job and being interviewed divided by the probability of being interviewed. So in this case, you have the probability of the job and the interview of 0.025 or 0.25. And we're going to divide that by the probability of you having the interview. So 0.1. And so we're going to divide that out. Uh-oh, something's not right. Let's read this again. Among those who interview, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered the job is 0.25. Alright, so yeah, we did this correctly, but we typed it in a little bit wrong. And the reason why I knew it was off is because I got a probability of 2.5, which is greater than 1. So let's do it like this. Alright, so basically the 0.25 is the probability that you're given the job given that you were interviewed. So that's 0.0 or 0.25. And that equals the probability of getting the job and being interviewed, which is technically the same thing because it's just getting the job, divided by the probability of being interviewed. Well, the probability of being interviewed was 0.1. Alright, so to figure out the probability of getting the job, let me do it like that. So the probability of getting the job, which means that you're also interviewed, so job and interviewed, is simply 0.25 times 0.1. And so if I do that over here, we're going to get 0.025 as our probability. All right, I hope that makes sense. I hope I didn't confuse you too much on that one. All right, so this last one is talking about independent events, and it says, according to recent figures from the U.S. Census Bureau, the percentage of people under the age 18 was 23.5% in New York, 25.8% for Chicago, 26.0% for L.A. If one person is selected from each city, what's the probability that all of them are under 18? Well, these events are what we call independent because they have no bearing on each other. If you're selected from, let's say, New York, that's not going to change the percentage of people under 18 in Chicago or LA. Whether or not you're 18 in a particular city doesn't affect the chances of you being 18 in another city because you can't be selecting the same person. So because they're independent events, I can simply just multiply the probabilities. So 0.235 times 0.258 times 0.26. All right, and if I multiply these all together, I get 0.016. And so then the next question says, are these events unusual? Remember from before we said an unusual event is less than 0.05. So I'd say yes, since the probability is less than 0.05, this is an unusual event. Which kind of makes sense, because if I was to select a person from 3 different cities and all of them just happen to be under 18, that's highly unlikely. All right, I hope this all makes sense. Email me if you have any questions.